Hey guys, how's it going? So I'm going to be starting this mathematical physics kind of lecture series, if you will. And we're going to go through several central ideas and some foundational concepts. But what we want to start with really is translating the homogeneity of space, the idea of Galilean relativity, and also we'll talk about restrictions to motion. So if you have a free particle versus a particle that's restricted, has restricted motion or anything like that, this is going to lead naturally to the appearance of mathematical objects like the form of kinetic energy, the appearance of the Riemannian metric, and there should be two n's there, and finally just the idea of a geodesic equation. And you'll quickly see why this is mathematical physics and not just some theoretical physics idea. So what we first know from theoretical physics is that an empty space has no preferred position. So we can think about the Lagrangian itself being a function of purely just for a free particle. It doesn't really depend on where the particle actually is, just how fast it's moving. And this generalized velocity, or this happens to be the temporal derivative of that coordinate. Sorry, that was my computer. But the conjugate momentum, then we can define as simply taking the derivative of the Lagrangian with respect to that generalized velocity. Okay? And taking the partial derivative, because that'll give us, essentially allow us to define the Lagrangian, or define the conjugate momentum in this way, in this general mathematical sense. So if we consider a second inertial observer in some system that is moving with some constant velocity relative to the first, in non-relativistic physics, the coordinates for different frames can be expressed as such, where v with constant v, with some constant velocity that's relative to the first velocity. And so the entire system just makes sure that the velocities add. So dq is equivalent to tq plus v. And to be really clear, this is something that we would call a Galilean boost. And it's a transformation that we're doing onto this Lagrangian. So we're saying if the physics is the same for all inertial observers, then L prime should just be, LQ plus capital V as a function of Q plus capital V. And these things, this must be physically equivalent to the very first Lagrangian, no matter the frame that we choose. Now, because they're physically equivalent, the equations of motion are going to be unchanged as well. And the two Lagrangians should differ by some total time derivative. So what we'd have then, from this transformation, is we would have that the Lagrangian minus q here should give us a total time derivative of some function. And, there exists some function f such that the difference between the Lagrangian should be the total time derivative of this function. Now we are going to require this. We're going to require this first equation to hold for all constant v. So holds, and let's get used to using logical notation for all constant v. Okay, just so we have nice shorthand. But at least, well, okay, holds for all constant v. Infinitesimally. Okay. Now what we can do is expand. We can expand this this quantity here. This quantity as a small boost, with a small boost as the variation of v. And now, what this would look like is if we take L q dot plus the variation of v. This should be equivalent to LQ dot plus Q dot variation V plus higher order terms in V. Okay. Now, the right-hand side of this equation here can likewise be written as the variation of v with respect to the total time derivative of some function k. And the reason why is because the total time derivative must vanish when v is equal to 0. So we're essentially saying that when delta v equals 0, this total time derivative will vanish itself. Okay, and so that will lead to an order of f to be equivalent to the variation of v times some function of q dot and t. And if we equate this, if we equate everything to the higher order terms, this will give us something called the infinitesimal symmetry condition. And the infinitesimal symmetry condition tells us that the derivative of the Lagrangian multiplied by this variation of v should be equivalent to the variation of v times the total time derivative of this k coordinate, which implies that the momentum as a function of q dot should be equivalent to this function, valid for any trajectory. For any trajectory q of t. Okay? Because we're doing the Galilean boost for some very small delta v. Okay? So that's the whole point of separating out delta v with or for rewriting this left-hand side in terms of this arbitrary function here. All right. Now, once we've encoded the Galilean invariance, what we can do is now restrict this momentum function. Okay, and in order to do that, we have to note that momentum. So note, momentum depends only on q. And let's just kind of separate ourselves here. So it depends only on q dot. And, you know, we have that this right-hand side here, this equation, let's call it equation 2. This equation here for it to hold for an arbitrary path, it can't contain, this K cannot contain Q double dot. Otherwise, this would introduce something that cannot be controlled or canceled by a function of Q dot alone, and that's called an off-shell identity. The K must depend on, at most, K depends on, at most, Q and T. So K is equivalent to K, Q, T. And the total derivative would be delta K over delta Q, Q dot, plus delta K over dt. And equation 2 then becomes P of Q dot, the partial derivative of K with respect to Q, Q dot, plus dk dtk. And here we'll arrive at equation 3. Now, this left-hand side, again, is a pure function of Q dot, and this right-hand side involves some Q and T as well, through the partial derivatives of K. But the only way that this identity here, the only way that this equation can actually hold is, for all values of Q, T, and Q dot, which can be chosen, independently if you choose some suitable path. The coefficients, these two coefficients have to be constants and independent of Q. So let's say these coefficients here should be equivalent to M, and then this coefficient here equivalent to C, with M, C being, real constants, okay? And if you integrate them, then you would arrive at the fact that the function itself should be linear, plus constant. And that this equation here will force the momentum. This equation here, if we, if we set this equation and we use equation 3, then it forces the momentum here to be affine. So now the momentum is forced to be, and it's restricted to be affine. And from this momentum, then, we can now get kinetic energy. So the Lagrangian, let's keep working down here. The Lagrangian is the integral of the momentum with respect to the velocity. So we can take, using the wrong one. So if we integrate the momentum, from our equation 4 here, we should be left with a similar result that we have seen in the past, which is that we get mq dot squared plus cq dot plus a constant. And the term c here, this is a total time derivative you can think of that as a total time derivative because there's a constant, and it doesn't affect the equations of motion. So this constant term is totally physically irrelevant. So what we would say then is up to gauge terms the Lagrangian for a free particle. So we just say up to gauge, the Lagrangian for a free particle is 1/2 m q dot squared. And so this is just the familiar quadratic energy, or the quadratic kinetic energy. And we didn't actually use any ad hoc assumptions. We forced it by the requirement of a Galilean boost here. And that simply adds a constant velocity. And so because there's a constant velocity, that's a symmetry of the action. If we let the constant velocity become a symmetry of the action, then that's the case that the momentum must respond linearly to a velocity change. It must respond linearly to a velocity change, and that if you integrate, or that velocity addition is linear in Newtonian physics. So if you integrate the momentum law, that would yield a quadratic kinetic energy. So you would have, so for just regular Newtonian mechanics, P equals mv, and then integrating that, you would get 1/2 mv squared. Okay, for just the pure kinetic energy term in Newtonian. Now, why that's important to note is because this is the cornerstone for really everything that follows. Because now what we can do is we can work with some kind of we can work with a system in a uniform gravitational field. Just delineate where we were working from. So now what we can do is place a particle in a uniform gravitational field and force it to live on a curve. Let's say we have an ambient space. An ambient space that the particle is in. Let's say the xz plane with Euclidean metric. And potential minus mgz. Now the particle is going to be constrained to a parabola, so we'll just take z to be alpha x squared, and the position is going to be completely determined by some generalized coordinates, x here. So we'll take x as the generalized coordinate, and we can parameterize the curve by having it as this ordered pair, and the velocity is tangent to the curve, so we're just taking r dot, would be dr vector to be 1 to alpha x dot. And this should imply to us that, or let's have this imply to us that z dot should be 2 alpha x, and then chain rule x dot. Now after doing this, we can substitute this tangent velocity into a ambient type of Lagrangian. So to first let's work with the Lagrangian in the ambient space. So let's say Lagrangian ambient space is 1/2 mx dot squared plus z dot squared minus mgz. Okay? And alright, so now that we've done that, we have expressions for z, and those expressions for z, let's just work with a kinetic energy term for now, which should be 1/2 m and then x dot squared plus to alpha x dot squared, and that should be equivalent to some 1 minus m 1 plus 4 alpha squared x squared. Okay, and this factor of x is multiplying everything, and that gives us a induced metric. Now, the induced metric, what that looks like is if we have some arc length element that is parameterized in, let's just say it's in Euclidean space. Oops, that's my alarm. Anyways, so the element, the arc length element in Euclidean space would just be this. But if we had 1/2 1 plus, if we were to induce a metric that constrains the particle's motion onto this parabola, we'd get this kind of term out here that's kind of funny, and this is a metric. This is a Riemannian metric. So it would have the notation like this, to be 1 plus 4 alpha squared. And what that does is it makes sure, the reason why we do this is because it ensures that the kinetic energy is still of the form 1/2 mds dt squared, right? It's 1/2 velocity squared, but the arc length element now carries the geometry of the parabola itself. That's important to realize because the potential function is going to be 1/2 mgz, which is 1/2 mg alpha x squared. And the full constrained Lagrangian is going to be 1/2 mgg x squared minus mg alpha x squared, because z is alpha x squared. That's the constrained Lagrangian. All right. Now notice, if we were to just kind of visualize this parabola, let's see, here's x, and then here's z. It's alpha x squared. So if we were to notice, let's say, let's take the system to be x is approximately 0. What happens when x is approximately 0? The free particle is going to be harmonically oscillating between, it's going to be approximately Euclidean itself. The metric is going to be Euclidean, because if you plugged in x to 0 there, it would just give you the did I do this right? There's a mistake here. Yeah, there's a mistake here. Where is eraser? Boop. Easy fix though. That should be an x squared, dx squared. Okay, so this would be Euclidean if we send x to 0, the metric or the curvature just becomes 1. And so as you get really close to 0, the curvature, there's really no parabolic curvature that's happening. And so what's nice about that is the Lagrangian would become approximately, let's say at x is approximately 0, the Lagrangian becomes 1/2 mx squared minus 1/2 mg alpha x squared. And this harmonic oscillator Lagrangian will become 1/2 mx squared plus 1/2 mwx x squared. And these usually give the equation for the equation of motion. it gives it in terms of the angular frequency squared. That's the acceleration of the generalized coordinate would be multiplied by the coordinate and its angular frequency. And if you compare the coefficients of this harmonic oscillator for a Lagrangian versus these guys here, you could just set them equal to each other and solve for the angular frequency. Which is pretty interesting. Okay? And we can get the exact equation too. So we got the harmonic oscillator case, but let's get the exact equation for the parabola. And the Euler-Lagrange equation is going to look something like the derivative of mgxx. Remember, we have a one-dimensional Riemannian metric times 1/2 m g prime xx is squared plus g prime. Okay, and then 2mg alpha x, where prime is the spatial derivative. And if we simplify this out, we can have gxx x double dot plus 1/2, or because we have to do a chain rule, or sorry, product rule. So gxx here minus 1/2 g prime x dot squared plus 2g alpha x is equivalent to 0. 1 plus 4 alpha x squared. There's our curvature term. Plus 4 alpha squared x dot squared plus 2g alpha x equals 0. And this term, again, really, well, that's the term for the curvature, but we also have this extra kind of position that comes from the derivative of the metric. And if we were to rewrite the equation in a standard kind of like Newton plus geometry form, we could rewrite it as this instead as this geodesic equation with the Christoffel symbol, 1/2 minus mg with our indices up top times the derivative of the potential with respect to x with the Christoffel symbol being equivalent to 1/2 which would give us the contraction of the indices since we're only in one dimension. This Christoffel symbol here, I mean, it looks kind of fancy, but by viewing it this way, this is a very basic example of how we get this is encoding some kind of physical message, which is that the wire is going to reshape what this wire or this parabola, it reshapes what straight ahead means. So if you were an observer, right, using this x coordinate, using only the x coordinate, and traveling along this parabola, you're going to perceive an extra acceleration here that is really just the projection of free fall onto the curved constraint. It's really just the projection of free fall onto a curved constraint. Okay? So what we can now do is remove gravity entirely. And let's work on something like a particle that is constrained really only by a surface of a sphere. So a particle that's constrained on the surface of a sphere with radius r. Okay, so this is a particle that's on a surface and is constrained to this surface. Okay? And the ambient metric, so now we can just work directly with the metric, it's going to be Euclidean, so let's just say x squared plus dy squared plus dz squared. But if you use spherical coordinates, x is equivalent to r sine theta cosine phi, y is r sine theta sine phi, and then z is r cosine theta. The induced metric on the sphere is going to be sine squared theta d phi. And your Riemannian metric as a matrix will look like this. And the Lagrangian for a free particle will be 1/2 m with the metric here times our quadratic energy, which would be equivalent to just 1/2 mr of the angular velocity, basically, plus sine squared theta. Well, really the polar angular velocity and the azimuthal angular velocity. Okay? And what you can do is find, or you can treat theta and phi as the generalized coordinates instead. So, for theta, we can have the derivative of the Lagrangian here to be equivalent to 1/2 mr theta dot, and the derivative of this to be mr theta double dot, and the derivative with just respect to the coordinate, the theta coordinate, sine theta cosine theta d phi d phi dot. Okay. Then what happens is the Euler-Lagrange is going to give us m r squared theta double dot minus mr squared sine theta cosine theta phi squared is equivalent to 0, which gives us the equation of motion for the polar coordinate. Let's write it as sine theta cosine theta azimuthal velocity squared. And then for the azimuth, we'll have the derivative of the Lagrangian with respect to this should be equal to 1/2 mr sine squared there times the derivative of the Lagrangian with respect to, or the time derivative, just basically using the Euler-Lagrange equations, assuming that you know how to plug them in. right? Oh, and we'll also do plus sine squared theta, the azimuthal acceleration, and then dl d theta, or sorry, dl d phi equals 0. So, you know, putting this all together for the Euler-Lagrange equations, we should have, because there's no potential term really coming from the azimuth, what we then have is that mr. So even though it's constrained to a sphere, we're not getting really any terms that are dependent on this generalized type of potential here. Now, we are getting a velocity-dependent thing that comes purely from the sinusoidal or from the trigonometric ratios. So that kind of serves as your little effective, not effective potential, but like it's like a potential term that serves just the curvature of the sphere. Sine theta squared d double dot should be equivalent to 0, which then gives us that phi double dot plus 2 cotangent of regular theta dot phi dot is equal to 0. Okay, so we have these two results. We have this one, and then we also have this one. Now, if we look at those equations pretty carefully, the general equations, or the general Euler-Lagrange equations for a Lagrangian should be a geodesic equation. Okay, so in general, for this Lagrangian, 1/2 ij with our quadratic, with our coordinates quadratically kind of mixed. This gives us exactly. This should give us the Euler-Lagrange equations with the Christoffel symbols permuting the indices here. And the Christoffel symbols are actually given by the metric itself. So we'd have Kij to be equivalent to 1/2 GKL with the partial with respect to I of GLJ plus J to be the ILth component, and then the LJ to be the LIJ to be this index. And then so for example, our metric that we chose, right, using the general formula for our metric, if we just look at the phi coordinate, that would be, so G theta theta would be, I'm sorry, what did I just write the real numbers? G theta theta would be R squared, right? And then G phi, that would be sorry, we're still have lower indices. So for the lower indices, it would be sine squared. Sorry, I haven't taken general relativity in a while. I took general relativity like 2 years ago. But yeah, and then you have these upper indices that basically, for the upper indices, you would want to take the inversion of them. Okay. Oh, and we also want the upper indices to be the inverse here, right? And the only non-vanishing derivative that you will find when you put them through the Christoffel symbols is that the you'll get that the partial with respect to theta of g phi should be equal to r squared sine theta cosine theta. That's really the one that's not vanishing here. So the non-zero connection coefficients, if you take theta phi, this should be 1/2 of g theta del theta del phi to be 1/2 to r squared sine theta cosine theta, which is equivalent to 1/2 sine theta cosine theta. And then if you do the same thing for phi here, this actually happens to be symmetric. I'll let you go through the formula yourself, but this should be equivalent to 1/2 g phi times taking the theta derivative of g phi low index, which would be 2r squared sine theta squared times 2r squared should be sine theta cosine theta. So we have a sine squared on the bottom, so we should just be left with cotangent theta. And if you substitute this into the geodesic equation up here, then you will be left with theta double dot plus the Christoffel symbol here from our non-zero connection coefficients, and that should be equivalent to 0, so that therefore theta double dot is equivalent to sine theta cosine theta plus sine, or plus the azimuthal velocity there, and then we'll do the same thing. So this shouldn't super surprise you, but it's important to understand. Super surprise you. This shouldn't leave you feeling super surprised. Let me English here. But this is expected. Because we know that the sphere intrinsically itself intrinsically carries with it a metric, and this metric itself has its own Riemannian geometry. And so, no forces are acting on the sphere. You just have a free particle that's just, moving on a sphere, doing its thing. Then it's just going to keep moving straight, but on a sphere, moving straight while remaining on the surface here, if it's just moving straight, or even something like this or something like this. What that leaves you with is things called great circles. And this apparent acceleration that you have on the great circle, these terms that you have for these accelerating terms simply exist not because they're new forces, but because the coordinate basis vectors, del theta and del phi, they rotate. Okay, they rotate as a particle moves. So the Christoffel symbols, here, they encode exactly that rotation. So in the intrinsic sense, one could say that the covariant acceleration is equivalent to 0, and that the particle's velocity itself, the particle's intrinsic, velocity, is being sorry, that was a really bad drawing, but the particle's velocity is being parallel transported. All right. So everything that we've covered, this seems like a lot of different unrelated things, but this is kind of the foundation, hopefully, from the mechanical concepts of mathematical physics, because we started really from just spatial homogeneity and Galilean invariance to then the fact that kinetic energy is quadratic in flat space, all right? But then we played around with constraint surface, with a surface that constrains, or really, first of all, going with just constraint one-dimensional types of lines in an ambient space, and then the ambient space here would be R3, but our constraints here would be the surface of the sphere. And so really this ds here can be written as some delta a b dx a by dx b, since we're only working in theta and phi, and the radius is a constant. And this metric here basically encodes from this Lagrangian the automatic production of the geodesic equation. So if a potential is present, then the right-hand side will become something similar to having a potential term. And really the key inside of this is that the kinetic term always has a metric form of it always has a metric form of this, right? The kinetic energy, that's super important. And constraints will simply replace that flat Euclidean metric by the induced metric of the constraint surface. And the connection coefficients are the mathematical residue of the fact that the straight ahead direction that you have here varies across a curved space. And so both the parabola and the sphere, they're not really these separate phenomena, but you have these manifestations of the geometric principle that a free particle moves along geodesics of the configuration space metric. Okay? So we started with symmetry, the idea of, motion and tangent motion, and then this just inexorably led to Riemannian geometry in the fairly limited language of mechanics that we have. But this is really the deep reason why a particle chooses to follow geometry. All right, thank you for watching.